where patients were randomized to one of two treatments. And we're going to see how we can interpret the results based on what you have learned in the past 2 weeks. So this is going to be a very interactive class. I expect you to supply me all the answers, under the hope that you have learned something in the past 2 weeks. So that's the first paper we're going to review. The second paper will be this paper here, where we're going to critique aspects of it based on what we know so far about survival analysis. So first, let's go on to the first paper, which is the New England Journal of Medicine paper. So let's quickly look at the methodology quickly, and then we can go on to discuss the study. So to give us a very high-level overview of the study design, let's look at this paragraph. Please read the paragraph, and somebody should explain to us in lay terms what's going on, so that we all have a baseline understanding of what the study is all about. So the paragraph we're reading is this one here. This is just this first paragraph. So I'll give you 30 seconds to read that, and then we can have somebody who will explain to us what the study is all about. Okay, that's time up. All right, so who wants to explain? Maybe let's do it this way. Let's break down some of these key terms here so we can understand what it's all about. What's a phase 3 study? What's an open label study? What's a randomized trial? And what were the treatment arms in the study? So let's start with phase 3. What's a phase 3 study? This is not our main discussion point, so let's get about that quickly so that we'll get to the main essence of our discussion. But we don't want to assume that everybody knows this thing, so let's quickly clarify those terms. So what's a phase 3 study? Okay, I wasn't expecting it's going to get complicated that fast. Let's see, maybe the answer's in the chat. Oh, okay, not very many. Okay, interesting. Okay, so in general, we have the phases of a trial. We have phase 1, 2, 3, 4. What does phase 1? What's the job of phase 1 trial? What does it do? So we have an overview of what we're talking about. In phase 1, what are we looking at? And you can unmute yourself and answer too. This is going to be a very long session. I can see this.
Somebody saying clinical trial.
Okay. All right. So, all right, I'll just explain it. So a clinical trial is think of it as a journey. A journey of drug discovery, right? At the end of the whole process is we want to create a drug that will give to human beings, or I'm just using human beings as pharmaceutical trials as an example. There are obviously many type of trials that we could do. Our goal is to produce a treatment, a medication that will give to human beings like you and I to take and to be safe and to get well from whatever is ailing them. So as you can imagine, we can't just go to the Amazon rainforest, grab some trees and just give them to humans, right? It has to go through a whole series of tests to make sure that it is not only safe, but it's also efficacious. There are two things we look for in clinical trials. Is it safe? And does it work? I mean, obviously, if I'm having a headache, I want a drug to cure my headache, but I don't want to be relieved of my headache and then get cancer. That's not a good trade-off at all, right? So I need the drug to be both safe and to be efficacious. Efficacy simply means how well does a drug work under controlled environments. So in phase 1, we're asking the question, how much of this dose can we give to human beings that will work? We're just starting from issues of dosing, right? We need to assess how much dose a human being can take. So that's the main job of a phase 1 trial, right? So if that's the main job of a phase 1 trial, do you think we should give that drug at that point to many people or just a few people, just from common sense?
Few people.
Do you think phase 1 involved? Sorry?
Few people. About 30.
Why does that make sense? Why will you give it to few people?
Because we don't know the safety of the drug yet.
Excellent. Now, do you think we'll give it to people who are will you give it at that point? Will you give it to healthy people or to sick people?
Healthy people, sir.
Healthy people.
Exactly, because you don't know whether this drug is going to kill somebody who's already immunocompromised. You don't want to now kill them, right? So the job of a phase 1 trial is to help us determine dosing, right? Safety, like what is this? What's a safe dose to give to humans? Now in the
Prof,
phase 2,
is it at that point that they give it to animals?
no. Animal studies precede human studies. You can think of animal studies as phase 0, but we're just focusing on, human trials now. So, in phase 2, now in phase 1, we know that, okay, this drug, this is the dose we can give to humans. In phase 2, we proceed to assess for mainly efficacy. Now that we know it's kind of safe, now in phase 2, does it work? All right. If a drug is supposed to, for example, treat lung cancer, does it do the job it's supposed to do? Now, at this phase, do you think we should give the drug to healthy people or sick people?
Sick people.
So that sick people who have the condition of interest, right? That's what we do. And the goal
More number of people
is
too.
of efficacy, right? So phase 1 trials are typically very small, maybe 10 people, 12 people. Phase 2 trials tend to be larger, maybe a few hundreds of people. Phase 3 trials are also called confirmatory trials, right? Now that's the big deal. That is the studies upon which drugs are approved.
Effectiveness.
So in the phase 3 trial, we're looking at both efficacy and safety. Now, what's the difference between efficacy and effectiveness? I heard somebody say effectiveness. What's the difference between those two things? Effectiveness versus efficacy. What's the difference?
Efficacy is in a controlled environment.
Excellent.
Whereas
So,
effectiveness is in real life experience,
great.
Scenario.
So when we're assessing in a clinical trial, what are we assessing then? Is it effectiveness or efficacy?
Effectiveness.
Both.
It's effectiveness.
Efficacy.
You guys just define it and then you cannot apply it back. You said that it is the performance of a drug under controlled conditions. That's just what you just told us now. So I'm just asking you now. I'm just asking the question a different way. That's so in a clinical trial, what are we assessing? Is it effectiveness or efficacy?
Effectiveness.
Efficacy.
Efficacy.
So it means you guys don't understand what you just told me.
Efficacy.
Clinical trial is a controlled environment.
All right, so we need to understand what we're saying, okay? We can't say that it is a performance under controlled conditions. And then when we are asked, so what are we assessing? We would now say the opposite. A clinical trial is a controlled environment. It's controlled because if the patient is supposed to receive 2 milligrams, they receive exactly 2 milligrams. If they're supposed to receive it at 2 a.m., they receive it exactly at 2 a.m., right? So it's controlled. Not like in the real world where the patient, takes it whenever they want or how much dose they want, right? That is not controlled at all. So in a phase 3 or a confirmatory trial, we're looking at both safety and efficacy, right? So this is supposed to be a phase 3 trial. It's global, meaning that it's patients from around the world. It's open label. Who can quickly explain that for us?
Open label means it's not blinded. So
not blinded.
Okay. All right.
The randomization process is not blinded.
All right, great. So it's open label. Now, what are some from a study design perspective and from a bias perspective? Because whatever we do in study design, we have to be worried about bias. You have to always think about bias. So what concerns would you have with the fact that the study is open label?
Bias. There could be
bias. We want to avoid selection bias.
All right, so that we have just one person speaking at a time. If you can just kindly raise your hand so the moderator picks one person who will answer, so it's more controlled. All right, so what concerns would we have with the fact that the study is open label?
Okay, Emmanuel.
So in open label, we try to avoid there could be a selection bias because it's not blinded. So either the participant is aware of the selection of the randomization process, so in open label we have such, but if it's blinded, then it could be one person blinded or two person blinded.
So in the case of open label, the study it means that it's not blinded to who and to who.
Abisoye,
So
you
it
want
means-
to speak?
Okay, thank you, sir. Open label, both the patient, the participants, and the researchers, they know what is given to each participant. So you could actually create reporting bias because you know what probably you are biased against what you expect, and you know what this patient is getting. So there's tendency to maybe you assess or it's
Excellent.
you just want to. Sorry.
Yeah, you're correct. So let's look at it from the dual perspective. So the doctor is not blinded, the patient is not blinded. What could be let's take them one at a time, right? The doctor who is not blinded, or whoever the investigator is that is not blinded. What's the problem with that? You've said it again, but we want to tease out the two parts separately. So the fact that the investigator or the blinded, what's the issue?
Ogumboye, your hand is up. You can speak.
Okay, thank you. Yeah, one for on the side of the investigator, there may be differential assessment of a particular measure because the researcher is aware that this person has particular or is exposed. So as such, he may tend to measure that more carefully among those exposed group, different from those who the unexposed group. That is on the part of investigator. On the part of the
Excellent.
patient, on the part of the participant, for the fact they know that they are exposed, it's just like when you're talking about case control, they tend to have more recall of issues. They could over exaggerate their responses just because they think that, okay, by doing that, they are going to be helped, or their cases is going to be if it's in treatment, they are going to get more benefit, maybe cure. So as such, there will be differential response from the participants who are exposed or who are not exposed, or who have the event that of interest, and those who do not have the event of interest.
Excellent. Apart from over-reporting or differential reporting on the part of patients, what else could the patients do?
Taiwo, you can respond.
Okay, good evening, everyone.
Good evening.
Hello.
Okay, so my own contribution actually has to do with the selection. The investigator, if they know a patient that is ill, they want to assign the person to the treatment rather than the control. So that will create a form of selection bias. That is what I have in mind. Then the other issue with the participants, if they know that they are assigned to the treatment, they may give false report about the subjective symptoms. They may report that they are feeling better because they know that they are on the treatment arm of the research instead of the.
Now, if you are a patient who was randomized to take the whatever, maybe it's a placebo, right? Of course, let's put aside the ethical issues of assigning placebo to patients. Let's just assume you're on a placebo and you are aware that this is a placebo and you're very, very sick. What are you very likely to do?
Okay. Lawrence, you want to respond?
Yes.
Okay.
I think the placebo effect will no longer be effective in that patient because he believes he's not receiving anything.
Okay.
Since he's aware that he's receiving just a placebo.
Okay, thanks. But I'm more interested in an action on the part of the patient now.
Ogumboye, your hand is up again.
Yeah, so I believe that the participant may cross to the other group because they may be feeling unhappy to remain where they are, or if they have choice and they are aware of the medication the other group the other group, like the treatment group is taking, and they are being allocated to the control group, they may want to cross over to the other group.
Exactly. So all of these things could result in contamination. Now let's move on to the next part of the methodology. What does this mean? That randomization was stratified on the basis of this, or this. Who can quickly explain that for us so that we can now move on to the major aspects of the study that involves survival analysis? So what does this mean in practice? So imagine that we're back in time and we're doing this in practice. What does this mean in practical terms? What did they do?
Okay. Ayobami.
Thank you, Prof. I think what you mean is based on clinical staging. If they are stratified, that means each of the clinical stage will be given different, or the distribution will be along the class or the number of stage that they have. If they have 1, 2, 3, 4, that means each of those stage we have different portion or different dose or different will be administered to them. That's what I think it means.
Okay, thanks. All right, let's do it practically, step by step. So based on information here, step 1, do what? Step 2, do what? So let's talk about what's step 1.
Okay, Sonia.
Okay, I think step 1, first of all, you stratify them, like you select them into the various strata randomly based on this stage of the tumor. And then after doing the
Okay,
randomization,
hold
having
on.
them.
Before you move on to step 1, you said you stratify them randomly. Is it random? I mean, we already have the criteria here. So is it random? John Shokas, can you kindly mute yourself?
Because it's
Ili, are you able to mute everyone?
Yes, I'm doing that now.
Can I go ahead?
Yes, please go. Go ahead.
All right. So the randomization is done at strata level. That's meaning we're going to have a bigger sample in this case. So the various strata, I think here there will be 3. First of all, you have the clinical tumor stage, the renal function, and then the tumor expression level. So those are the 3 different strata that we'll be having. And then the persons in that group will be selected randomly into that strata which they fall into.
All right, Sonia. Okay, let's pause there. You said we have 3 strata. Does everyone agree that we have 3 strata here?
Taiwo.
that it's 3 strata we have here?
You have yes responses in the chat.
No, the answer is false. We don't have 3 strata. How many
Yes,
strata do
two.
we have?
No.
2 strata.
2 strata, that's false. How many strata do we have? The information is right here.
Top dance.
Someone says 6.
Excellent. How is it 6? That person should
Each
explain
of
to
them,
us why it's 6 strata.
each of them are divided into 2. Each of the different subgroup are divided into 2. Like
So
the
we
first
have
one,
3 characteristics. Clinical tumor, there are 2 groups. Renal function,
yes, 2.
and the last one, the tumor expression, 2 groups. 2 times 2 is what? 4. 4 times, sorry,
Yeah.
2 times 2 is 4. 4 times 2 is 8. Sorry, that's not 6. You're going to have 8 strata, right? You have to multiply the 3 of them. So 2 times 2 is 4. 4 times 2 is 8. So that means that you're going to have unique subgroups. So you're going to have individual this value and this value, and so each combination, unique combination, will be a separate stratum. Do we all get that?
No, sir. Kindly repeat that, Prof. I didn't get that.
Okay. So if you have 3 characteristics, right? And each characteristic has 2 categories. So to get a number of strata you're going to have across the whole study, you have to multiply across all of them. So 2 times 2 is 4. 4 times 2 is 8. Do you understand?
Why not just 2, 2, 2? Since each group is 2, 2.
Okay,
So
so
why
let's say,
not 2, 2, 2? Why not 6?
all right, so it's because you have, let's open an Excel spreadsheet here quickly. So we have group 1. Can you see my screen, my spreadsheet here?
Yes, sir.
So group 1,
Yes, yes,
2,
sir.
and or let's say characteristic 1, characteristic 2, and characteristic 3. So here you have 2 groups, A and B. Here you have C and D. Here you have E and F. So you have to create unique combinations for each of those. So the first will be individuals who have A here, C on the second one, E on the second one, the third one, A on the first one, D on the second one, E on the second one, and all the, so you are creating unique combinations of every single value. So that's what strata means. Strata means that the groups are mutually exclusive. And so in the study, we have 3 characteristics, each of which have 2. If you create unique combinations of each of those individuals, then you're going to have 8 groups. Does that make sense? Are we still confused?
Yes, it does now.
Okay.
No,
So that's step 1, right?
no.
So
Please, I
step
have a
1,
question.
yes, please go ahead.
That's like
Okay,
2 combination 3.
Sorry. Hello? Can I?
Yeah,
If you
Christopher,
go
yeah, go
by,
ahead.
two combination
if you go
theory.
by what you just said, Prof, there are other combinations that can also emerge apart from these 2 you just created. Like we can have B, D, F, which is not among the ones we created. So I believe if we do what you just explained now, we may have more than even 8.
So A, C, and E is the same thing as E, C, and A. They are the same thing because they are individuals who have that same characteristic. So you're not counting duplications of groups. All right, this is your homework. Please just go and try this at home and see how many unique groups you create so that we don't spend time on that. All right, so step 1 is create the unique strata, right? So now we've created the 8 strata involved. What's the next step? Because remember, we're told that the study involved one-to-one randomization stratified on the basis of these three characteristics. So what's the next step now? We have our 8 groups, 1 to 8. What's the next step?
Okay.
Within each group, what do we then do?
Someone say randomization within.
Randomization.
All right, we need one person to answer, please.
Can raise your hand. Bunai. Bunai, you can speak. Are you unable to unmute? Okay, Sonia, you can go ahead.
Okay, now that we've created the groups, then we begin to select individuals to fix into those groups using the method of randomization in order to avoid bias.
What
That's
groups are you
individuals
referring-
with those characteristics in the
Sure,
different
so
groups.
what groups are you randomizing to
So
now?
that's stage 2. The strata, this AC.
No, these groups, okay, I think there's some confusion here. These 8 groups already contain people. Let's say in this group you have 200 people, in this group you have 150 or 100, in the next group you have 30. Assignment of people into strata is not random. It's based on their characteristics that they have, right? So you have all these people here. You're not the one assigning them into the strata. They're already assigned based on the characteristics that we have identified. That's what stratification means. So we already have all these individuals in this group. So the question is, what's the next step?
The next step is to randomize them into the 2 arms in each of the
Excellent.
strata.
Excellent. So we can choose to say that we're going to randomize people at random to, so 50% will be randomized to treatment, the first treatment, and the second will be randomized to the second treatment. Why do you think, why do we stratify? Why did we have to go through all this headache of creating 8 strata in the first place? Why is that done? Research.
To avoid bias.
Okay, I'm not necessarily.
Confounders.
Sorry?
Confounders, so minimize confounding. Confounding
there's already a randomized trial, so we're not worried about that. Randomization itself will have taken care of that. Why do we stratify?
Can I speak, sir?
Yes, please go ahead.
Yeah, we stratify to ensure that the sample is representative, because you want to ensure that all the possible groups that are different are included in your final sample in the treatment and the control group, rather.
Excellent. So that's the main reason, is to ensure we have enough individuals in these groups so that when we are doing our analysis later on, we can analyze within the subgroups. Because it's possible that just by luck, all the individuals in ACE could have been randomized to treatment 1, and there's nobody of this group in treatment 2. We obviously will not want that. So if these variables are important to us, we stratify so that when we're doing our analysis later, we are guaranteed that there will be people in each of these groups for both the treatments and the control. So that's the reason why we stratify. It's not that it enhances validity, not that it reduces bias. It's to ensure that we have a sufficient number of people so that when we're doing our analysis later, we can have sufficient individuals to use in those groups. All right. So now we have a good sense of the design of a study. Let's go to what we are really our business for today. which was to interpret survival curves, to interpret Kaplan-Meier curves, and see how the results can be interpreted based on our understanding from the past 2 weeks. In general, when you're reading a study, especially a randomized trial, you want to make sure that you have a sense of the two groups, like how well was the randomization. So it's always a good thing to look at table 1, which tells you the two study groups, in this case, treatment A and its comparison and its control group, right? So here you have the distribution by various characteristics like age and sex. So here, for example, we see that the median age and the range is 65 years and versus 66 years, right? The ranges are provided in the brackets. From what you can see here, do you think the randomization was well done? Was it balanced from what you can see here? It's not a trick question. Was it balanced on roughly? Can you say that the groups are balanced?
Yes.
Yes.
Excellent. And from the context of epidemiology, what are we trying to achieve here? What randomization is trying to achieve? Exchangeability, right? Who can explain to us what exchangeability is? From our classes on causal inferences, what is exchangeability?
Anyone? No hand. Oh,
What?
okay.
Okay.
Ogunboye, your hand is up.
Okay, I will start from the first thing you asked, that what are we trying to achieve? Randomization first is trying to eliminate known and unknown confounder in this study. And the other one is I don't had is there a change or
Exchangeability, yes.
exchangeability? It means that if we exchange the group, like the people in the treatment group move to the control group, and the people in the control group are moved to the treatment group, it is also possible to be able to get the same result in the long for the study.
Okay, you get the idea. Just from the English word exchangeable, what does that imply? Let's just focus on just the English language, the meaning of when you say something is exchangeable, just from common sense or just intuition, what does it sound like?
It means that A can replace B, B can replace A.
Excellent. So it means that these guys that receive treatment, if we took them and said, oh, we're not going to give you treatment, you are going to be control group, the results among the treated would be exactly as what we see in the untreated if these guys had been untreated, right? The same thing here with the comparison group. The results we see among the comparison group would have been exactly as those who received the treatment if they had been treated. So in a counterfactual scenario, right, this is just in our head, but we're saying in a hypothetical scenario that we switch the treatment, the outcomes will have been exactly the same as the other group, right? So the whole idea of randomization is to ensure that the two groups are exchangeable, that this group and this group are exactly the same in all respects, except what?
Except intervention.
Exactly. So that's the premise. So that is what we're trying to achieve, that these two groups are exactly the same in every other single way, except the treatment. So that if we're going to say, oh, these groups differed, the only explanation is that treatment was the only explanation. We don't want other alternative explanations that, oh, well, that other group had more men in them. No. They are balanced in all respects except the treatment. So that is essentially what we're trying to achieve. Now, from the perspective of equity, when you look at this study that claimed to be a global study, what concerns do you find, or what criticism can you level against the study from a representation perspective? Remember, the study was described as being a global study. What can you infer about the globalness of the study?
More whites and Asians are in the study than blacks and other tribes.
Exactly. So you can say, okay, you can argue that to what extent are these findings kind of representative to other non-white or non-Asian populations, right? So that's something that, we can, so these are some of the things we want to look at when we're interpreting studies. But now let's go on to the main issue of the day, which was our survival analysis and looking at how we can interpret the curve. So first of all, let's go on and see how well we can remember this. So soft questions first. What is the name of this? What do we call this curve again?
Kaplan-Meier.
What's the name of this? Excellent. Kaplan-Meier curve. The y-axis of a Kaplan-Meier curve represents what?
I think it represents the survival probability.
Percentage of patients.
Okay, survival probability, but specifically it represents the cumulative survival probability, right? Okay. And then the x-axis represents what?
The time to event.
Time to event, yeah.
Excellent. Now, all right. Now, just from high level, right? What do we infer from these two curves? The orange curve. Don't worry about the treatment. The fact that the orange curve is on top, what does that tell us?
The survival is higher for that group.
Better outcome.
Exactly.
Survival is better.
So exactly. Survival is better. It has a more favorable survival. Think of two people wrestling. Typically the person at the top is the one who's winning, right? So the orange curve is on top. So that means that it's winning. It has a favorable survival compared to the comparison. Now, when we look at the slope, right, of this curve, as if you remember the hypothetical example we drew, you had very drastic curves that were like staircases. When you contrast it to a curve that looks like a staircase, what can you infer? Why is one looking like a gentle slope and the other one looking like a staircase? What's the inference from that? Because these are the first things you want to look at when you're looking at a survival curve. How is the shape? Is it like almost like flat like this, or is it at very sharp angles, like a staircase? So what does this tell us here?
Can I speak, sir?
Yes, please go ahead.
Yeah.
Okay, the one with steady slope indicates that the event of interest happened gradually in that group. For instance, maybe death is the event of interest. So that means the number of people that die as you move from along the gradient of the of time to event, fewer people are dying in each occasion. Whereas the one that has a drastic or a drastic step pattern, it means at that point or period, there's a high number of people that have the event of interest, perhaps death. So,
all right, thank you. All right, let's make this more visual, right? Let's create a contrast here. Oh, this is rather small. Let me take another screenshot. All right, so imagine that we have a graph that is steep. So this is obviously very different from what we see here, right? You can see that this one is it's a very gentle slope. This one this one looks like a staircase. So when you compare this one versus this one, which graph has events occurring more dramatically or a lot more at one single time?
The one
you created.
Exactly. So remember that this part of a curve, this one here represents where events are happening. So if the drop is very long, that means that you have a lot of events happening. You can see how this one here, see how gentle the curves are. You just have, a few events, and it's remember the flat part of the curve tells you there are no events happening there, right? The tags here, what do they tell you? The vertical tags along, what do they tell you? Which are things like
lost to follow up.
Exactly. These are censored observations. So you should be able to, when you look at it, when you take a Kaplan-Meier curve, first things first, look at which one who is winning, who is at the top, right? Next thing, okay, how much censorship do we have? Next thing, how's the overall slope of the curve? Is it very drastic, meaning that you have a lot of events happening, or is it just more tapered, right? Indicating that the events are very, more rare in terms of the occurrence. So we've established that the orange guys are winning because they're on top. We've established that the events are generally quite occurring quite frequently, so that you have just few events per unit time. Now we have a line here drawn at the 12-month point, and perhaps the authors are trying to compare survival at the 12 months between the blue guys and the orange guys. What kind of test will you need to use to compare survival in this manner? What kind of test will that be from what we covered in class last week?
That will be z-test.
Excellent. Somebody is saying log rank test. Log rank test. Is that a correct answer? Why or why not?
It is z-test because if you are comparing two groups at the same can you hear me, sir?
Yeah, but it's a very often.
Okay,
all right.
Let me say it again. So it is z-test because you are comparing at one specific point in time or a duration. Okay, but if you are comparing the two groups throughout the whole program and throughout the whole study, from the beginning of the study to the end, then you can use the log rank test for comparing the two groups.
Excellent. That's very correct. So since here we're looking at one point in time, that will be a z-test. If we're looking at the entire study period and comparing the two survival curves throughout the study periods, then we can use the log rank test. Now let's look at the part of this table here. Here they're reporting the number of patients with events divided by the total number. And so here we have the treatment and its control. So from common sense, the group with the highest survival will have, in terms of the hazard ratio, what will it be? What will you expect? You should be able to relate the Kaplan-Meier curve to the results from Cox regression, right? So if we compare this, since these ones have a better survival, it means that the hazard ratio will be less than or more than 1. Which one? Will it be more than 1 or will it be less than 1?
Should be high, more than 1.
All right, let me repeat the question. The orange guys have a better survival, we said, right? As we can see, because they're on top. So when we compare this group to the comparison, do you expect the hazard ratio for these guys in relation to this comparison to be more than 1 or less than 1?
Less than 1.
You should be able to
the risk will be less than 1.
Less than
exactly.
1.
And why is that so? Who remembers the definition of hazard ratio? How do we define the hazard ratio?
Yeah, I know it's a probability. It's a measure of the probability of an event occurring. And since it's a probability, it should be between 0 and 1. Between 0 and 1. 1 means that the event is 100% possible, while anything that is less than 1 it has the probability. Okay, So in this case, it should be like.
All right, let's calculate these hazard ratios. We have the number of events in the treatment group and the control group. In the treatment group, we have 533 individuals, 187 of them developed events. In the control group, we had 246 who developed the event out of 530, right? If we calculated the ratios, what will we get? And how does that compare to this value? Let me pull up a calculator. Actually, let's do that together. Do I have a calculator here? All right, let me just pull up this. So here we have, on the first arm, we have 187 out of 187 divided by 533, right? All divided by 246, all over 530. So we get the result here as 0.7. Can you see my screen, the status screen here?
Yes, sir.
Okay, great. So we have the result here as 0.75. But here we have it as 0.68. Who can explain to us the discrepancy? Why do we have this result not matching up? Is it an error? Why? Why do we have, when we take the actual number of events that occurred, we get a different result, and when we calculate it from the hazard ratio, we get a different number? What explains that phenomenon?
I think probably there are some missing data.
No, it's not missing data. Any other explanation? Okay, what are we calculating here? The way we've calculated this, what is this? What measure is this? Epidemiologically. Total number of events that have occurred.
The proportion.
No, so here, right? Total number of events that have occurred in the treatment arm, or divided by total, the rate of occurrence in the other. What do we call that? So, well, in other words, this is the risk in the treated and the risk in the untreated. Please mute ourselves. There's a terrible echo going on here. Thank you. So we have a risk in one group divided by the risk in the other. What do we call a ratio of risk?
Rate ratio.
So what we've calculated here is the relative risk, or a risk ratio. But what we have here is a hazard ratio, right? What's the difference? Like, what have we failed to account for in our calculation here?
Those censored, those that are censored.
Well, not necessarily. In a way, it's related, but there's something more nuanced that we're looking for. Because you have the same number of events accounted for, right? The total number of events accounted here for has indirectly accounted for censoring already. But there is something very important we are not taking account of here, which is reflected
time to event.
Time. Yeah, exactly, time. We are assuming that, well, they all go to the end, but we're not asking the question, when did they get there, right? It's like you have runners on the racetrack. The first group is super fast. They run within 10 minutes. They all got to the end of a race. And then you have another group who are very slow. They got to the end of a race at the last 10 minutes. In this calculation, we're treating all of them as the same, right? But when we talk about hazard ratios, we're talking about the instantaneous risk that the individual develops the outcome, given that they have not yet developed it. So we're interested in not just risk in general, but instantaneous, like in an instant, which has to do with the time element, right? So not all events are born equal. Like we need to account, and that's what is special about the hazard ratio. It accounts for the rate at which the events occur, which is not what we find in the risk ratio, right? There's no accounting for that element. And so this is why if you calculate it manually here, you might not necessarily see the same event here, because they are different things. Now, who can interpret this result for us? We have hazard ratio for events is 0.68 with 95% confidence intervals, 0.56 to 0.82. Who can interpret that for us?
Okay, Ali.
Yes, I think it is the risk of people dying or getting the event of the requirement is a 68% with a confidence level of 0.5% significant level.
Okay, thanks. But you said it's 68%. That is not quite true. That is wrong. You want to rephrase it?
The chance of getting is 68% with a confidence level of 0.05%. No, with b value of 0.05.
Okay, thank you. How about you remove the word percentage from your explanation? Can you try again, but remove the word percent and replace it with the word times?
Oh, times. Okay. The chance of the event being seen is a 0.68 times higher with confidence level.
All right, thanks. You've tried. Who wants to help her? Thank you very much for
God's will.
I think the chance of the event happening is if the event is there, it's 0.68 and less likely. It can be more because it's not 1. So if you want to explain percentage, you say 1 minus 0.68, which is around 32%. Less likely because it's not.
Okay, excellent. So we can say that the risk of the outcome here, which is mortality or whatever it is 0.68 times lower among the individuals on this treatment compared to the control group. And that was statistically significant because why can we conclude that it's statistically significant? What about the confidence intervals can lead us to that conclusion?
It's less than 1.
Instead of you saying it's less than 1, I want another one.
Because it does not include 1.
Exactly. It does not include 1, which tells us that it is statistically significant. Now, here we have the median survival. For this treatment, we have NR. What does this mean? There's a hand up.
Chisom, you want to go again? Or is an old hand?
Okay, so what does it mean?
Anyone?
We have here.
Not reached.
Okay, what does that mean from what we can see here?
So it's indicating a.
All right. Let's take it this way.
It's NR is indicating. Okay.
All right, Charles. Let's take it this way. How do you calculate the median survival time? Where should we start from? Which axis should we start from? Y-axis or X-axis?
I think it's the X-axis. The X-axis speaks to.
We'll start from the Y-axis.
Yeah, we'll start from the Y-axis because the final answer we're interested in is time. So if the final, if we want to land is time, then that means that we must start from where?
Y-axis.
Exactly. If we want to land on the X-axis eventually, which is the answer, that means that we must start from the opposite, right? So since it's median, where on the Y-axis should we start?
50.
Exactly. So we'll start from 50 here. Let me take a screenshot of this. So we start from 50 here, and we draw a straight line. Sorry, my line is not very straight, but let's make sure it's straight. All right. So what inferences can you make on this with this line? So we draw a straight line until where it hits the group, right? And then we can say that that is a survival. So for example, for the blue guys, where does it hit? Where does this line first hit the blue line? It's around this place, right? So we can say that it's somewhere around here.
42. 40.
Yeah, we can never be accurate now unless we use software, but we know that it's somewhere around here, right? That this event occurs, right? Now, what of the orange guys? Where does it hit the group?
Nowhere.
Exactly. And that's why you have not reached. Why doesn't it hit the group?
Because we need more time.
And why do you need more time?
Because the number of events are very few in the yeah.
When we say median survival, we are saying that at least half of the people, right, have died, have experienced the event. If not up to half of the people have not experienced the event, is it mathematically possible to calculate the median survival? What do you think?
It's not possible.
It's not possible, right? So this is what has happened. And why is it that up to half of the people may not yet have developed the outcome? What are some of the possible reasons?
Survival is higher.
Okay. Or
with
what
the
else?
efficacy of the drug.
Okay. The
study duration may also be low.
Exactly. Study duration may be low. Excellent. What else?
Someone said lost to follow up.
Exactly. We may have a lot of censorship, right? For all those reasons, we may be unable to calculate a median survival. So in that case, we might say, okay, we're not able to do that. So let's calculate, for example, instead of calculating the median, which is the Q2, we might say, okay, let's calculate the third quartile or whatever reason, right? Or we may just say we're going to report the median, but for other group that we cannot access, we're just going to say it was never reached. You have a lot of options to pick from, right? But those are some of the things, we should be able to tell when we read a paper that has survival analysis, reported in it. And then here we have subgroup analysis for event-free survival, right? Who can interpret this result for us? So first things first, have a practice that before you jump into reading things, make sure you always read the title first, right? So what does subgroup analysis mean in this context? And why might we want to do that?
Subgroup analysis here shows that you are looking at different characteristics and checking out what is the survival within each of the characteristics. So in terms of race, in terms of sex, you are doing a subgroup analysis.
Okay, so can you take, let's say this male, let's say sex, right? Can you interpret this for us, please? Or anybody?
So for male,
subgroup is those groups with.
All right, Sonia, we cannot hear you. Your audio is really bad, so we'll go to somebody else.
Taiwo, your hand was up.
Yes, from what I can see here, the hazard ratio is lower for the female compared to the male. And I think that to suggest that the survivor is better among the females compared to the males.
Okay, but I want you to interpret this results. The standard way we will interpret results. You know, the risk was zero, you know, XXX among this group compared to that group. Like, that's how I want it to be interpreted. Who can interpret this result for us?
Let me try, Prof.
Charles?
Okay, go ahead.
Yes. So the male the male is the male has a reduced event risk at 0.71 compared to the female, which showed 0.56.
Okay. Thanks, but that is incorrect. Who wants to take it? Who wants to take a stab at it?
Prof, I want to try.
Please go ahead, Theo.
Okay. So looking at the gender, you can say that of the males, they have a 0.71 times higher risk of developing the outcome compared to the females. And in terms of statistical significance, looking at the confidence interval, since it's between 0.58 to 0.88, you can see that it's significant.
Okay, thanks, but that's wrong. Anybody else want to try?
Yeah, looking at male alone as a subgroup, the hazard ratio is 0.71, meaning that the risk of death among male that took the intervention or the drug is 0.71, that of those that do not take the intervention.
You are almost there, but can you be? This is the treatment, right? We have this treatment and a control.
Yeah.
Can you be very precise, please?
So among the males, the risk of death among males that took or that were exposed to the drug durvalumab is 0.71, that of those that did not take the drug, meaning that the risk of death is about 29 about 29% less among those that took the drug compared to those that did not take the drug.
Thank you. Are we comparing them to women?
No, we are not.
So we're comparing men to who? Men to men. So men who were on treatment, this treatment, versus men who were on the control group. This is the whole point of subgroup analysis. This is why you don't have reference groups here, because this is also why you have an overall result here. This is saying in the whole population, all patients, men and female combined, those who took the treatment had 0.68 times lower risk of developing the event compared to men and female who did not take the drug, who were on the other treatment, right? So this is subgroup analysis. Now, why would we want to do the subgroup analysis? Why would we do that? What's the interest here?
Charles, your hand is up. Okay. Ogumbo, yeah?
Yes, the reason why you want to do subgroup analysis is to actually check for confounder, because those subgroup characteristics like race, sex may be a confounder or an effect modifier in this study. So you want to check and you want to know exactly which one they are.
Okay, thanks. Thank you very much, but that's incorrect.
Okay, let me try. I didn't know my mic was off. Prof, let me try.
Okay.
Okay, so the reason for the subgroup, I think, is, in analyzing the trials, is to evaluate the effectiveness of the the intervention, across different patient characteristics.
Okay,
I think
thank you.
that's the reason.
Now I want to go back to the previous answer. You mentioned something, that it's assessed for confounding. But then you also mentioned another very interesting word, which we should not forget, which is effect modification. Your answer suggested that somehow those two things were the same. What's the difference in how we assess for confounding from how we assess for effect modification? What's the difference? In both of them, we're comparing one thing to the other. What two things are we comparing when we're assessing for confounding? And what two things are we comparing when we're assessing for effect modification? Ogumbo, do you still want to go back to your answer and revise it?
Yes, and I'm really stuck. Yeah, but
okay,
I know that effect confounder.
Okay, don't worry, I'll help you. So
Okay.
in confounding, right, we are comparing crude results versus what?
Okay, adjusted results. Yeah.
Take the two results, crude results, and you compare to adjusted. If they are very different, at least 10%, 20%, you say, oh, wow. The adjusted results are very different from the crude, right? And so this suggests that this variable is a confounder. So this is classically how we assess for confounding. You compare crude and adjusted, right? Is that what's happening here? Ogunboye, back to you.
No,
is
sir.
that no, that's not what we're doing here. It can't be assessment for confounding, right? So we're assessing for effect modification. So in effect modification, what we're doing, we are still comparing the results, but among different groups of the outcome, right? So we're comparing, for example, this group versus that group to see where they're different, right? So that's effect modification. We're comparing, again, both confounding and effect modification involve a comparison. For confounding, we're comparing crude, adjusted. For effect modification, we're comparing, for example, males versus females. We're seeing, are the results different? Is the relationship between A and B different among males versus among females? So that's the difference. Now, we also must realize that effect modification is something that we want to see. It's a desirable thing. We are hypothesizing that, well, maybe there's a biologic mechanism where this treatment works differently among males and females, right? So it's something we are exploring to see. Now, when we are doing that, what should we be aware of? Is there a theory? That must be a really funny joke, but please mute yourself. Judging from the very wide confidence intervals, what should we be at? What is the concern when we are doing this kind of subgroup analysis? What is the issue here?
Ogumboye, is that
number, sample size.
Sample size.
Sample size,
yeah.
right? Remember that at the beginning of our study, right, we calculated our sample size based on we want to find the effects overall. This is what we calculated our sample size for. This group here, all patients, this first row, all patients, that's what we calculated our sample size. Now, let's go back and redo the sample size and let's see the problems we run into. Let's use this as our effects in measures, right? Let's say that our study is equipped to detect this difference. Let me quickly calculate that and let's see the problems we do run into when we so let's look at the sample size calculation and let's see, please, engineer, can you kindly mute yourself, please? So let's do a quick sample size calculation and let's see the problems we run into with this. So let's assume that our study is powered to detect these differences. So we have the prevalence or the incidence of the treatment among the treatment group is 33.8 and among the control group is 25.8. So let's use that as a basis to see the minimum number of people we need in each group. So our study here is a comparative study with 2 arms, percentage as outcome. This is a randomized controlled trial. The prevalence of outcome among the non-treated group or the control group, we're going to use this number, 25.8, right? The prevalence or incidence among the treated group is 33.8. Let's just round it up to 35%. Level of confidence 95 is going to be a 2-sided test. The power desired is, let's say, 80%. Let's make it, 80%. And the ratio of treated to non-treated based on the methodology was 1:1. We assume a 10% attrition rate, which means a 90% response rate. Based on that, the sample size required is 437 individuals in each arm. That is what the number of people we need to detect a difference, if we're assuming that this is the treatment effect we need, right? When we look at the groups, we see that at the overall level, the treatment, we have 533 people here and 530 people. Excellent. We can easily detect differences because the minimum sample size we need based on these parameters is 437 individuals in each treatment arm. Now, let's see, however, what happens when we get to the other smaller groups. For example, among let's pick some really small groups here. Among people who are non-white, you have 165 people in one group and 150 in one group. Among people who are among this group, previous receipt of BCG therapy, you have 31 versus 26. This is a far cry. 26 people in one arm, that is a far cry from the 437 people you need minimum, right? So the biggest problem with the subgroup analysis, especially when you have this main number of groups, is you are running into an issue of both type 1 error and type 2 error. Who can explain to us why you run the risk of both type 1 and type 2 error? Type 2 error should be very apparent because that's just what we just described, right? What is the implication of type 2 error here?
False negative.
Can I try?
Sebastian,
False negative.
Yes, Sebastian.
The risk of false negative.
Which means what in simple terms?
Itaiwo.
Yeah, for type 2 error here, it means that there are significant differences that we cannot detect because of the small sample size.
Thank you. Now let's look at this group, right? Taiwo, while I still have you on the line, let's look at this group, right? Previous BCG therapy, yes. Can you just describe what you see here? And contrast that to BCG, no. What do you actually see on this graph? And tie that back to type 2 error.
Okay, for the previous BCG therapy, which is yes, I know there are very few people in both groups, which is not up to the 430 something that we calculated in a sample size. That means that we cannot detect any difference. And that is why the confidence interval is very wide. There's imprecision there.
Okay. So because the confidence interval is very, very wide, complete the sentence. I need to read my because the confidence interval is
it crosses the one line, making it non-significant.
Exactly. Now it's possible that in reality, if we had very large sample size. Now, when we contrast that to this other group, what do we see in contrast?
In this group, the sample size is larger, is close, it's even more than what we calculated. Therefore, I think it's more precise. The confidence interval is narrow.
Confidence interval.
Exactly. Now, you see, in the real world, right, you can see some of the dangers that can now emerge from unwarranted subgroup analysis. Imagine that you are making a recommendation to a healthcare agency that's in charge of reimbursement for treatment. And you now tell them, well, there's no evidence that we should only reimburse patients who who have, no to this answer, all these people with this wide confidence interval that are non-significant, we cannot reimburse their treatment because there's no evidence that the treatment works for them. Now, would that be why would that be such a dangerous statement to make or a dangerous recommendation to make?
It will be dangerous because in those people where there appear to be no significant effect size, is because the sample size is low. Assuming that the sample size is sufficient, it may be possible to detect those differences.
Excellent. So we said that when we have this kind of very extensive analysis, we run into two problems. On one hand, we have the issue of type 2 error, where we'll have very wide confidence intervals, and we might end up declaring results that would have been significant and non-significant. But we also have another problem, right? So that means that in this kind of extensive subgroup analysis, if we see a result that is not significant, we can't 100% say that it's not significant because, like the saying goes, the absence of evidence is not evidence of absence, right? Now, what are results that are significant? Are we 100% sure that they are truly significant when we have this kind of extensive subgroup analysis? Yes or no, and why?
Abiswe.
Okay, thank you very much, sir. It's no. It could just be that we have so many people that the sample size is so large that it made a difference, that does not exist to now become, obvious.
Okay, thanks. But the explanation here is not because of a sample size per se, it's because of another phenomenon. Which is it? Remember, we're doing so many tests, right? So many subgroups. What does that ring? What bells does that ring in your head? Once you start seeing so many subgroup analysis, what should be the alarm bell ringing in your head?
It may mean that we are trying to detect what is not there.
We are looking too hard.
Exactly. When we're looking too hard, what kind of error do we call that? What kind of statistical error is that?
That is type 1 error.
Exactly. So type 1 error. So see the dilemma we are in now, right? If the results are not statistically significant, we cannot say for sure that they're significant because it could be type 1 error. It could just be that we found something because we're looking so hard. And if results end up being non-significant, we can't actually say they're non-significant truly because it could just be that we're not powered. So this is why when you're doing subgroup analysis, it has to be intentional. You must tell us beforehand, right, in the protocol that these are the subgroups you want to do. Because remember that the whole point of subgroup analysis is to detect, effect modification. So it's not a mistaken, you don't just, wake up and say, oh, I'm just going to do a million subgroup analysis and decide which ones I'm going to go with. You must have written that in the protocol upfront, way ahead of time. So that means that we require you to be quite deliberate. There has to be some intellectual commitment to this so that you think thoroughly and say, based on biological behavior or biological, precedent, where do I expect that you might see some differences in biological response from this treatment? Well, I think that it could be on this group. So you define this upfront, and this takes us back to stratification. If you have interest in looking at certain subgroups, you might want to stratify on them to ensure that you have enough people across all of them. But keep in mind that, when you have so many subgroup analysis, you run the risk of both type 1 error and type 2 error. Those two could coexist, So you want to read results. You don't want to take the results of a subgroup analysis so religiously to heart and say, oh, wow, this is the word of God. No, you have to take them in context that, well, we're just going to interpret them qualitatively, right? And just know that, okay, it tells us some kind of direction, but it's not as if we're going to take them to the bank, because what the study was prepared for right from the beginning was, this all patients. That's what we calculated our sample size for. That's what we did every single thing for, right? And that's why we cannot be too over enthusiastic about subgroup analysis, right? So in a nutshell, right, this is how you want to, interpret results from from, survival analysis and some of the things you want to take to mind as you're reading them. Now, I shared a second paper with you. Please take your time to read that critically. The point I was trying to make here was, this is a cross-sectional study where the authors try to use some fancy methodology. I guess they really want to call this a survival analysis, right? So we can discuss this some other time, since we are, short of time. But please do read it very carefully, and you can drop your comments on our LinkedIn page of what you think about the methodology. The whole point here we really want to establish is that you should not ask of the data more than what data are able to provide, right? If data was just cross-sectional, don't start twisting your head 360 degrees to just introduce a fancy methodology, right? And this is something which sometimes, people who are very, new to research, or people who are, new PhD graduates, sometimes they really want to show that, oh, wow, I know methodology. And so even when the methodology is not appropriate, they really want to force it in, right? So that was the whole point of sharing this paper, was to help us think through that process and say, what are some of the limitations of using this kind of methodology, right? It's all about modeling to create, as I call it, pseudo-longitudinal data, right? What are some of the limitations or challenges that could creep in with such a methodology? And why should we be very wary of such methodologies, right? Knowing fully well that the central mantra is, do not ask of the data more than what data can answer, right? If the data are cross-sectional, just use methods for cross-sectional data. If they're longitudinal, you can use methods for longitudinal data. So please read it, and I'll be very happy to hear your thoughts. You can drop your thoughts on our LinkedIn page for this class, and we can have a discussion on that. All right, at this point, I'm going to pause there and see if there are any questions that we can answer from the session.
Yeah, Prof, I have a question.
Okay.
For the type 2 error, could we not have defined the power of the research before commencing? In that way, we'll be able to eliminate type 2 error that may result.
Okay. So yes, we do define the power. We say the power is 80%, but the power is, remember, we calculate it among the overall population. What we're saying here is that this study, you have done what you said you were going to do, and now you're going to subgroup analysis. The power was defined for all patients, comparing treatment versus control. That was the sample size. When we calculate our sample size here, we are doing it for the entire study. But now what we're doing in subgroup analysis is not that. We are now going into each subgroup, including these people who have just, previous PCG, yes, these guys have 31 here and 26 here. And we're trying to do that. So your study is not equipped to answer all these questions you have started suddenly trying to answer, right? Your study was only prepared to answer this original question. So if you are interested in these other subgroups, well, you can commission a new study, right? You can say, okay, we're going to do a separate study that looks at this group. Or if you really, really want to make sure that, you account for those groups, well, then make sure that your sample size is powered adequately. So in this case, what you could do to the sample size is you can then adjust it by a factor of the smallest subgroup. What does that mean? It means that look at all the subgroups you want to analyze for, right? Now look at the smallest subgroup. So the smallest subgroup here is, let's say, individuals who say yes to previous BCG therapy. Now, what percentage are they of the entire population? Let's say they are, 9%, 0.09. Well, you then have to divide your overall sample size by 0.09, right? So if you had a sample size of, let's say, 800 people divided by 0.09, well, your new sample size is 8,888. So your sample size has jumped from 800 to a factor of 10, 8,000, from 8 to 8,000. So if you really, really want to incorporate analysis for those subgroups, well, you must make sure you account for them in the sample size by making necessary adjustments to the original sample size. If you're not making adjustments for that, then whatever interpretation you have here should be qualitative. So you see, they're not even showing the results here. You see, NC, non-calculable. They're not even showing results for very, very small groups. I believe they're not showing results for groups that are below that less than 30, right? But in general, you want to set standards and say, these are the subgroups we're going to analyze, and we've already prepared for them by accounting for sample size. But even then, you should be aware that there's still a risk for type 1 error. So if you're going to make those kind of extensive analysis, it's not just sample size you have to worry about. Because remember, these problems come as a pair. Type 1 error, type 2 error. So you can account for type 2 error by making adjustments for sample size, but you have to also account for type 1 error by adjusting the family error rates. For example, you can use a Bonferroni adjusted p-value, right? That accounts for, the number of groups you want to compare, right? So that your alpha threshold is no longer 0.05, but 0.05 divided by the number of groups, right? You can also say, well, we're going to set our instead of calculating 95% intervals, we're going to calculate 99% intervals so that they're wider and more likely to contain one. But you have to think through those issues. That's the point I'm trying to make. You must think intelligently about those issues, the kind of problems that could arise, and how you're going to manage them. I hope that answers your question. Next question, please.
Yes, thank you, sir.
Thank you,
Okay.
Prof.
So I have a question. Is it possible to do the same calculations for a rare event? And if it is also possible, maybe to use survival analysis for prediction, maybe you can be able to extrapolate the probabilities.
Well, if your outcome is a rare event, you might want to consider the study design entirely. The problem with a rare event is that it's rare. So if you are doing a prospective study to capture a rare event, well, you're going to be in that study for a long, long time. You either have to recruit a huge number of people and follow them for a very long period before you can even find one person, right? So that's why we have more efficient study design. This is the entire reason why the case control study was designed, to address issues like that where you have very rare events. Because in the case control study, you allow for the outcomes to accumulate before you do your study, right? So that you're not spending all your time following people and paying them money to follow over time. So some of these issues may not apply because it's a different study. You're not following people, so issues of loss to follow-up may not necessarily apply. But it's just thinking smart about the kind of design you use to answer specific questions based on the context.
Yeah, thank you for that. For this type of analysis, do we have to first of all run the normality test? And maybe if we find that our data is not compatible, our data does not meet the criteria for, let's say, the parametric test, do we have another version of survival analysis that can deal with non-parametric?
Survival analysis does not assume normality. Of course, survival data is always skewed. Survival is not normally distributed. It's skewed. So that what you have in mind perhaps might be linear regression. So yes, survival time is a continuous variable, but we also account for censoring. It's a special kind of analysis. So what you are concerned about is quite different, which is when you're analyzing continuous data, and you have to worry about normality, which is an assumption. So the underlying assumptions of a particular method dictate what we do. Survival analysis never made a claim about caring about normality, so don't worry about that, right? Linear regression, however, assumes that the data are normally distributed, so we want to test for normality. And then if they're not normally distributed, there are bunch of things we can do. We can transform the outcome. We can use another kind of regression like quartile regression or median regression, and a whole bunch of other things that we can do. So the underlying assumptions dictate what we do as far as diagnostic tests.
And maybe my last question, and maybe I didn't get it from the first lectures. How do you deal with the concern about deaths that may occur, maybe due to other reasons apart from what you are investigating? Let's say maybe we are investigating cancer, but along the line somebody died from something else apart from cancer. How do I account for that?
So we said, we addressed that in the first class, and we said there are many ways to handle them. One common way to handle them is to treat them as competing risks and to consider them as censored, because the individual it's like treating them like they're lost to follow up. So in other words, the guy who just packed his bags and left for Egypt, and this guy who just died from a road traffic accident, when you are interested in cancer deaths, are one and the same, because sure, he has died from the car hit him and he died, but that's not the death works. That's not an event of interest, because we're interested in something else. And that's why sometimes in studies you look at things like all-cause mortality, right, which is mortality from anything. This is similar to, like, even in this study here, you have something like overall survival, but then you also have another kind of survival, which is, like in this case, event-free survival. So sometimes you define, different kinds of outcomes, like primary outcome that is much restrictive or much more nuanced, and then you might have a broader outcome. It's your study, so you should feel empowered to define things as of course, assuming they make sense. But there are many ways that can be handled, and you can feel empowered to choose which one is one best to your liking and makes scientific sense.
And thank you for that. Do we consider the issue of the interaction between the subgroups? For instance, if we looked at age at randomization, and then there could be that interaction between that age of randomization and gender. So how does that play along? Or when we stratify, that is enough for us?
And that's why you have to look at table 1. Table 1 is supposed to help you know how well was your randomization performed, right? The beauty of randomization is that it takes care of both observed and non-observed, variables. So it shouldn't matter, right? Because it takes care of everything. Now, if it doesn't, well, your table 1 will tell you, and you can proceed accordingly. This is why we still collect variables, potential confounding variables, so that we can still adjust for them should there be evidence that our randomization was not balanced.
Thank you. Thank you.
You're welcome.
Thank you, Paul. Do we have anyone who wants to ask a question? No one? Okay. I shared the evaluation on the chat. Please do well to complete it before you leave.
All right. Thanks, everyone. Sorry?
No, I was trying to say I will share links to our social media platforms for those that are not there to join. Okay. Prof, I think we are good. There's no harm.
Okay. All right. Super. All right. Thanks, everyone. Enjoy the rest of your day.
Thank you, sir.
Thank you, Prof.
Bye-bye.
Thank you, Prof.
Thank you, sir. Bye.
Hello, Prof. Hello, Prof. Can we get the second materials?
Sorry?
Can we get the second materials? Second publication you use.
Yes, of course. They will be shared with you.
Thank you very much.
And yeah.
Thank you very
much.
You're welcome. Yeah. All right. Bye, everyone.
Thank you very much, Prof.
Yeah. Thank you.
Please kindly share the evaluation link again. The first one is not working, please.
Please check your network. It's working. I believe it's working. Just check.
In fact, I've not seen the evaluation.
You know, I'm having the same issue.
Yes.
What's the issue with
the
yes,
evaluation
Francis?
link?
Thank you. It's working. Yeah, it's on the
Yeah,
chat.
it's on the chat.
Yes. I just dropped it again.
Okay.
Yes. And yes, the PDF Prof shared on our WhatsApp group chat. We will share them. If you're not there, just join the group. We will share them again so that you can review them and make your comment.
May I speak? Hello.
Yes, please.
My own is an appeal on the two previous classes. That is today's one and the last one, the second and the third one, which is today's one. If we can get the recorded class, it will help us to listen to it. And
yes,
though I meant, secondly, hello?
Yes, I can hear you. Go ahead.
Secondly, though I drop in my own evaluation, I made a comment that the survival analysis tool is interesting for some of us, but for some of us in social sciences and all that, it's somehow technical. I don't know how it can be brought to our level if there will be another opportunity to consider maybe using other events that are of social, not of sciences that is so technical to us. I don't know whether you get my point.
Oh yes, I understand what you're saying. Well, sometimes Prof asks for opinion of what you want, like the topic you want us to discuss. I mean, if you have a topic that you want him to cover with in that line, you can make that suggestion, and Prof will be glad to take it.
Okay, so then how can I drop such a suggestion across
Are you
to
on our
him?
WhatsApp group?
That is I think what they call it, group, village
Chorus or village school?
Village School 2, that is the group I belong to.
Yes. All right.
Village
Yeah.
School
You
2.
can drop that suggestion there. It's
Okay.
okay. Just drop it there.
All right. Thank you
Femi,
very much.
you're asking that you should be added. You're welcome, sir. You're asking that you should be added to the group, the WhatsApp group. I just dropped the link. Just click the link and it will take you straight to the WhatsApp group. Femi, if you can hear me.
Yes.
Just click the link, WhatsApp. It will take you directly.
Thank you so much.
Just join. Yes, yes. You're welcome. And then the lectures are recorded on YouTube. Just go to YouTube and search Chisquares. Then go to live. All the lectures are recorded there. You'll find all the lectures there. You can follow up with those you missed. Okay, Usman, you want to say something? Are we all good? Are we all taking the evaluation?
We're on it.
Hello, sir. Hello,
Yes,
sir.
Usman, go ahead. Go ahead.
Just like the last speaker, he said that this survival analysis is very important for most especially public health, medicine, but not in social science. I try to find out where can I use this survival analysis in my field, library and information science. Up to now, I do not see it, sir. I agree with that person.
Hello.
Hello, sir.
Hello.
Are you with me?
Yes,
Sir?
yes.
Hello.
Please allow this
So
man to finish.
can I come in?
If someone can help me, Kuma,
Let him finish.
I'm waiting for someone to help me if I can use survival analysis in social science, like library and information science. Thank you, sir.
Thank you. Okay, it seems you wanted to respond to him, Nelson.
Yes. Survival analysis is not limited to public health alone. The only thing is that it bears different names in different fields, like those in social science. Social science, it is commonly used among those that are working in insurance, people that take that take loan. You can use it to estimate the survival rate. I mean, the time whether they will default or the time for repaying the loan. It can be used in any area, even like the library you mentioned now. The time spent in the library, it can be using the survival analysis. Even the way people are recruited into an organization, and the exit of the personnel from the organization, it is applicable even in agriculture, in every areas. Thank you.
Thank you, sir. I appreciate, sir. Thank you. Hello, sir. Hello.
Hello.
Thank you, sir. I appreciate.
Can I come in?
Okay, sir.